Okay, so this is homework 3, part D. What we're going to be doing today is looking at the Stefan Maxwell equation. As you can see here, so what the Stefan Maxwell equation is used for, right, is if you have a multi-component system, you're able to isolate two of those components, run tests on those, and see how those will relate, and then that can be used when looking at your multi-component system, right? So if you have like 5 components, right, and you take 2, you can then see how those will react with it within that 5-component system, right? It's not just those 2, right? And then you can do that for all of them, and then you can relate all of your components together, right? And so when we look at Stefan Maxwell, right, we have a couple of different variables here. We have our x, I, or j. We'll call it A, right? That is our mole fraction of the component, of a component, right? Next, we have this term here, right? That's our gradient of our chemical potential, not our viscosity, right? And typically, we work with mu being viscosity. Here, it is the gradient of our chemical potential, right? And in the Stefan Maxwell equation, that is our driving force, right? This whole term here is our driving force because we have that gradient on that side. Right, next we have our N, right? This is our molar flux of a component, right? So we have our I and our J, just like our X's there. Next we have our C, right? That's our total concentration. And then last we have our Dij, right? That is our diffusive constant. And this is the main form of Stefan Maxwell equation, but which is so important for chemical engineering, right? Because it allows us to relate those multi-component systems. Now, you can also write it in a couple of different ways, right? One of those ways, all of them have this on the left side, right? So I'm just going to refer this as the driving force, right? So dF. So one of the next main ones, right? We have our driving force, and that will be J equals 1 to N. And when we're looking at this, typically we're looking at gases, right? And so when we look at gases, this is actually a Y, right? So I will rewrite this as YI and YJ. It's X is typically used for liquid, Y is for gases. And so here we're going to look at gases, right? And so our next variation of this, right, is going to be using velocity. So we have our molar components, or our mole fractions, and then we multiply by our velocity of J minus the velocity of I all over our diffusive constant, right? So what we want to do here is we want to relate these two equations, right? So what's the first big thing we can notice? Right, in this equation down here, we are missing our concentration. So what are we going to do? We're going to multiply by our concentration, right? So when you do this, you have to multiply both the top and the bottom, because when you multiply both the top and the bottom, it doesn't affect the equation output, right? That would end up being 1, right? right? So we keep our yi, yj times our vj minus vi, and now it is concentration times ij, right? And so one thing to note here is, right, when we are multiplying things out, right, we know our concentration times our mole fraction, right? So C times yi in this case, that is just going to end up being the concentration of that component, right? So it'll be Ci, or with J, it'll be Cj, right? And so we can look at this and we can multiply this out and we will get um, um, df equals, right, the sum of, and it'll be yi times cj, right, times our vj, right, and then it is minus our yj ci vi all over cdij, right? And so when we're looking at this, when we're looking at the big picture here, we want to try and relate it back to this equation up here, right? So what's the difference right now between these two equations, right? This one has our flux, and then this one has our concentration times our velocity. What is flux, right? We think of flux, we think, all right, it is moving, right? So it has to have a speed, right? That's our velocity. And it is our molar flux, right? So it's our concentration times our velocity, right? And so this ends up being, right, Cj Vj, right? Concentration J times the velocity of J just equals the molar flux of J, right? And so we can then rewrite this equation, right? Our driving force equals, right, the sum of yi times nj minus yj ni all over concentration times diffusive constant. And if you compare these two equations, they're exactly the same, right? So we were able to connect these two Stefan Maxwell equations using what we already know, right? And so we can further do this, right? If we look at, right, if we look at what we were doing a lot in the last video, right? We used this equation here, right? Our molar flux equals our molar diffusive, right? J, right, plus our Y times our overall flux, right? This was something that we used a lot in the last video, right? We talked about how this can be used for other situations. Well, now we're going to use it with our Stefan Maxwell, right? So we know this, right? We have our Ni or our Nj, right? And so we can plug these in, right? So our driving force equals the sum of Yi times Jj plus Yj n minus our Yj times our Ji plus Yin all over our concentration times our Dij, right? And so we can multiply this out, right? And we'll get this here. I'll just multiply it out real quick, right? We have our Yijj plus Yijn minus Yjji plus Yjyin, right? So this is a minus, and so all over our Cdij. When we look at this, oh, I missed a y here. This is Yj. these two terms are the same, right? Cancel them out, right? Because we have our negative sign here. And so that then makes this equation df equals yijj minus yj ji all over cdij, right? And so using our equations that we have used before, right, we were able to get a third Stefan Maxwell equation that we were able to use if we have our molar diffusive flux, right? If we have that value, we can then use this one if we don't have the other terms, right? And so we were able to just plug in equations that we already knew and modify the Stefan Maxwell equation and further make it applicable depending on the situation you're in, right? So next, what we'll do is we'll move on and we'll talk about situations where the gradient of our chemical potential is at standard state, right? So we're going to copy this equation here, right? We'll just take our basic Stefan Maxwell. And what we're looking at here, right? What we're looking at here is this chemical potential, right? So what we're going to, this scenario, we're going to look at where the gradient of the chemical potential is equal to the gradient of the chemical potential, at standard state, right? That little circle up there represents standard state. But 90% of the time, or however often, that's not the case, right? So how do we remedy that? We have to multiply by our gas constant, our temperature, and then the natural log of our molar fraction, right? And so when we look at this, we know that the gradient's the driving force, right? So what's the driving force? It's just going to be our d over dz, right? And so when we do this, right, we can bring that over, right? And then we will end up with this here, or we take the derivative, right? We can take the derivative and end up with, sorry, this is wrong. We can take the derivative of this, right? And we get our d, and then it's our chemical potential at standard state plus RT ln xi all over dz, right? Well, we know that this is a constant, so when we are taking the derivative, that's just going to be 0, right? And so we can then write this as d. We can then write this as RT times 1 over xi right? We can write it we can write it like this, right? And so when we do this, we can then look at, or we can plug this in, right, back into this equation. And so we'll get xi RT 1 over xi dxi dz all over RT, right? We look at this, that cancels, this cancels. And so what we're left with on this left side, right, is our dxi over dz equals, right, the right side of our Stefan Maxwell, right? Our j equals 1 to the n of, we'll use yi and j minus yj and I all over cdij, right? And so, right, we were able to um, um, simplify this down to a standard with using standard state into a much simpler equation, right? And so when we move off of this, right, if we go back to this equation here, right, we can take this. So if we're looking at this here, right. So what do we know about molar components, right? They in a two-component system, which is what we're assuming this is, right? When we're assuming the gradients at standard state, in a two-component system, the sum of the gradient or the sum of the mole fractions has to equal 1, right? So yi plus yj equals 1. So you can write this as y minus, or 1 minus yi equals yj. You can do the same thing for the molar diffusive flux, just if they equal 0, right? So our ji plus our jj, right? So therefore, negative ji equals jj, right? And so we can plug these in, right, to kind of simplify this down in this our two component system, right? And so it is now yi times negative ji minus 1 minus yi ji over cd ij, right? I don't know why there's an equal sign there. That was wrong. Right. And so when we do this, right, we can multiply out to yi, negative yi ji times or minus 1 plus minus ji minus yiji, right? Plus yiji, all over cdij, right? And so we look at this, right? We look at this, and this, exact same, just negative and positive. Those cancel out. And so this is then rewritten as our driving force equals negative j I over CIDIJ, right? And so what's our driving force? That is our dxi over dz. So right now this might not look similar or familiar, but we can rearrange this equation to j, right? Ji equals negative cd times our dxi over dz. Well, this one should look familiar, right? This is our Fick's law. And so just by assuming that it's a two-component system and that our chemical potential is at standard state, we were able to simplify Stefan Maxwell's equation down to Fick's law, right? And so that kind of broadens the usefulness of Stefan Maxwell, right? We know that in different situations it can be adjusted, right? We adjusted it for velocities. We adjusted it for molar diffusive components. We adjusted it all in a two-component system all the way down to Fick's law, right? And so this overarching equation is just so useful because we're able to use it to identify parts of our component or parts of our system, right? Whether it's 5 components, 6 components, however many components, we can use it to relate things together. And so we can use that to see how these components interact with each other. And that's kind of why it's relevant, because we're able to use it in such a broad sense and in so many different ways, right? And so we were able to find the Stefan Maxwell with velocity, with molar diffusive constant. We then simplified it down in terms of when the gradient, or the gradient of chemical potential is at standard state. We were able to get an equation for that, right? And then finally, we were able to take it and turn it into Fick's law, right? And so that's everything for this video, and it just shows how useful that Stefan Maxwell actually is.